Hey everybody, welcome to week 4, our final week of the concepts of calculus, or as I like to call it, calculus camp. We have now taken quite a journey together, and I know some of these ideas are really kind of mind-blowing, and it's going to take a while for them to kind of percolate in your brain, and later you might say, oh wait, let me look back, I get this now. But today we're going to kind of embark into the other side of calculus, and you may already know kind of the nuts and bolts of how to do integrals, but hopefully you have already watched the 2 videos from 3 Blue, 1 Brown about what they are. And if you have not, actually go and watch those videos first, and then I'm going to clarify a few points from them and then have a little wrap up. So here we go. So the videos you watched already talk about what integrals are. And again, you may already know the nuts and bolts of how to find an integral, but what's more important is actually understanding what is it you're finding. When you actually compute a definite integral, what is that? And so there are a few things we should mention. I think the first one and the most obvious one is when you find the value of an integral, what you're finding is an area under a curve. And the 3 Blue, 1 Brown videos have such awesome animation that you can really see that. And you could see how we're adding up all these little rectangles and boom, we have this area. But that's not only what that area is. Yes, it is area, like in the sense of geometry, but that area actually has a meaning. For example, in the case of your function being velocity, as you saw in the video, then that integral is the distance you traveled. So that actually has a meaning. So if for any reason you know how something is changing, so you know a certain rate for it, you can figure out the change that has happened. In this case, how far your car went. That's pretty useful because sometimes we don't really know the function that governs a situation's behavior, but we can measure how fast it's changing. And if we can do that, we can find out how much has happened in a certain amount of time. That's pretty cool. But the biggest thing that links it all together, because this idea of integrals is kind of interesting, you know, being able to find an area that normally we couldn't. But the thing that makes it most useful and most powerful is that it actually links to what we've been doing for the last 3 weeks, and that is derivatives. So integrals at their heart are actually anti-derivatives. And I know that may not seem as shocking and surprising to you as it was to the founders of calculus, but that's a big deal. When you've spent all of your time studying rates of change, and then all of a sudden you realize that finding these areas are actually undoing derivatives. It all ties together, which is what makes it such a cool package. So those are the big ideas I hope you can walk away with in terms of integrals. That technically you're finding the area under a curve, but that area might have a meaning, like for example, distance traveled. And the way that we actually crunch those things out is using antiderivatives. That's awesome. So I want to bring up a little visual from the video where he talked about how that area is distance traveled. And I want to just talk a little bit more about this idea of integral notation. So let's break this apart a little bit more and kind of talk about what's there and what we're doing. So in your math classes, in Algebra 2, maybe in pre-calc, you learned about a symbol that looked like this. It's a Greek letter. It's a sigma. And so sigma means sum. So whenever you see that symbol, we know we're adding stuff up. And so, for example, let's say the formula here is 2x, and x is going from 1 to 4. So what sigma means is start at that bottom number, which is 1, plug it into your formula, so 2 times 1 is 2, and then plug in every number up to the top number. So we have 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and 2 times 4 is 8. And so the sigma means plug in those numbers and then add these up, which will give us a total of 20. That's what we know so far. If you want to add up things, you just need a sigma and you can add them up. But that's very limiting, there's that word again, because sigma can only go from a concrete number to another concrete number, and you don't deal with anything in between. So here's what's cool about an integral. The fact that it looks like a lazy S is not an accident, because that little lazy S kind of represents a sum also. But it's better, because remember, sigma, we just plugged in 1, 2, 3, 4. Well, you're going to plug in all the values on the interval from 0 to 8 into our function and add them all up. So it's taking the idea of what sigma does, but making it so much better. So instead of having maybe 4 numbers to add up, we have infinite numbers to add up. So what we are doing is adding up a whole bunch of v of t values, and every single one between 0 and 8. And that's why the graph looks like a solidly shaded region, because you have so many values you're adding up all together that there are no gaps anymore. And that's where this little guy is so important. And I know when we first learn about integrals, everyone says, what is that thing? What is that dt? Well, I hope as a result of the last 4 weeks, you understand dt is that little nudge, right? If you pick a specific place in this graph, like I've just chosen here, and then you say, okay, I'm going to go over just a tiny, tiny little bit, that is your dt. And we want that dt to get really, really, really small. That's the idea. So everything is about this idea of infinity. We are getting infinitely small, and what that's doing is making all of those little rectangles merge together and look like solid area. That's pretty awesome. So the key here with an integral is first remembering it is a sum, and then secondly, remembering that that dt is necessary because that is that little tiny nudge that we're letting get really, really small. So that's the idea of what we're doing. Now, the actual doing of it is not hard at all. Calculus itself is a very easy step-by-step process for most things, but really understanding what you've done, that's the cool part, and that's what takes a while to really soak up. So let's take a look at the other side of this. We know what theoretically we're finding when we find an integral, but then there's this idea of derivatives and antiderivatives, right? We know how to find a derivative. In fact, let's kind of go over the one we have here. So if you have t squared and you want its derivative, let's think what we do to get to that 2t. So first, we multiply by the exponent. So we bring that 2 down, and then we decrease the exponent by 1. So now instead of t to the second, we have t to the first. That's a derivative. Now, what if I want to go backwards? What if I want to start with 2t? How do I get back to what I started with? So we need to reverse the steps. Instead of the decreasing the exponent by 1, we need to add 1 to the exponent. So we're just doing the process backwards. So instead of t to the first, we now have t to the second. Now our second step is the original first step. Instead of multiplying by that exponent, we divide by that exponent. And I'm going to add the new exponent. So our new exponent is 2. So we would have 2 divided by 2, or just t squared. So it's the power rule backwards. And we can go backwards with any derivative we know, whether it's a trig function or e to the x or whatever it is. If you know how to do a derivative, then you can undo that to end up back where we started. So that's where we're going to bring what we've already been doing into this idea of integrals. So let's actually try one. So we know that we are thinking of this function here as a derivative of something. We don't know what the something is, but what we're doing is actually figuring out what did we start with. So we're going to do the analytical side of this, meaning we're going to crunch it out, and then we're going to talk about what we just did. So here we go. So remember what we do. We think about each term separately, and then we do that two-step process backwards. So right now we have 6x squared, right? X squared is going to bump up by 1 power and become x cubed. Then we're going to divide the 6 by that new power. So 6 divided by 3 is 2. Awesome. On to the next term. We have 2x to the first. So if we add 1 to that power, that's now x to the second. And then we divide by that power, so 2 divided by 2 is 1. So minus x squared. Now the constant's a little bit tricky, but remember there's an x to the 0 attached to all constants. So if we add 1 to the power, it's now x to the first. And if we divide by that new power, we just have a 1. And that's it. Now we talked about in the video also, technically there is a plus c at the end because there could have been a constant in the original and we don't know. But when we're doing a definite integral like this where we have a specific answer we're looking for, we don't worry about that plus c. So we are now going to plug our limits in. So what we have just found, we had the derivative. This is the antiderivative. You just went backwards. You did your rules all backwards. So as he showed in the video, what that means is we need to plug our values, our 0 and our 2, into this antiderivative. So here we go. So we're going to have 2 times 2 cubed minus 2 squared plus 2. And then we're going to plug 0 in. So we have 2 times 0 minus 0 plus 0. So we always plug the top number in first, bottom number second. All right, so now we just need to crunch this out. So we have 8 times 2, that's 16, minus 4 plus 2. And then, of course, everything in the second set of parentheses is just a 0. So final answer is 14. So that's the math side. It's pretty just concrete and step by step, and it's not hard, right? But what's a bigger question is, what did you just do? What is 14? What is that? So let's think about this problem again and think about it in terms of what you actually just did. So you've in practice, you found an antiderivative and did some number crunching, but what did you really do? So what we have here is a graph I made on Desmos of the 6x squared minus 2x plus 1 as a function. So I'm going to call this equals f of x. And this graph right here is f of x. So if you integrate from 0 to 2, graphically what you just did is here's my 2 value right here. So basically what you just did is you found this area that I'm kind of trying to shade in here. You found the area of this yellow shaded part. So what we know is that the area of that part is 14. So that's kind of cool. So area is 14. Now that gives it a little more context of what you just found, but it doesn't really give it any meaning, right? I mean, what is this? So let's think about this function a different way. So instead of thinking of x's, I'm going to switch all these x's to t's, and I'm going to say that this is our velocity function. So I'm going to erase what just happened here, and we're going to call this the v of t graph. And just for fun, let's put some units on this graph. So let's say on the t-axis, we are in minutes. And let's say on the v of t, we are in, let's say, feet per minute. Okay, so basically what we're talking about is a graph of how fast something's moving. And so when I look at this, I say, wow, this thing is speeding up super fast, right? We started about 1, and in no time at all, we are off the graph completely. So this thing is going at lightning speed, whatever it is. So we still know the area under that graph is 14, but what does that actually mean for this thing that is traveling at super fast speeds? Well, remember what that area is? It's actually the distance that this thing has traveled from time 0 to 2. Let's see why that makes sense. So first let's talk about area. Area is always kind of a length times a width situation. So what if I take the units on my t-axis and multiply them by the units on my v of t axis? So minutes times feet per minute. You see what happens there? The minutes cancel. I'm left with feet. So that kind of is telling me this area under a velocity graph is telling me a length, a distance. So 14 feet is the distance traveled from time 0 to time 2 minutes. And that's what you just found. So what a journey. Let's go back a minute. We started with, let's just do some math. We crunched it out. We got an answer. All good. But then we started thinking about, so what does that mean on a graph? And it means area. Well, that's kind of cool. But then we made it real life. And we said, if this is a velocity of something, you just found out how far that thing traveled from time 0 to 2. Pretty cool. And that's why integrals are so powerful. Not only do they find area, but they also interpret what that area means in real life scenarios. And we'll be learning a lot of that in calculus this year. So back to our graph that you saw in the video, where you're starting to fill in this space with rectangles. Now, this region that you see here is not one that we have a geometric formula for, right? And so filling in with rectangles obviously leaves a lot of gap space, and it's not so great. And the video explained to you why the more rectangles you get, the better. But here's where calculus can be really useful, and this idea of using rectangles to find these areas. These rectangles that you are seeing in this picture are called Riemann sums. When you use rectangles to fill a space to estimate area, we call that a Riemann sum. And you'll notice every single rectangle is touching the function on its upper left corner. You see that? So every rectangle is touching the curve on the left corner. So on the left side of the curve, these rectangles are too small. But once you go over the vertex, now these rectangles are too big. But either way, it's always the left side part of the rectangle touching. So in this picture, we have a left Riemann sum. You could also situate it so you'd have a right Riemann sum, where the right corner touches the curve. So which one's better, and where would we need these in a real life situation? Because you learned the actual calculus where we find the actual area, but sometimes we can't do that because we don't have a function. We just have some data points. So let's talk real life. What do you do when you have some real life data points, but you need the area under that curve and you don't even have a curve? Here we go. Let's take a look at this problem. So this is a very typical AP calculus sort of question where they say, okay, we have this function f of x, but I'm not going to tell you the equation of f of x. Sorry, you don't get that. But what you do get is information about f of x. So what we know is f is continuous. There are no breaks in it. And it has the values in our table. So let's kind of think about this. So our x values are going from 0 to 14, which definitely fits on my graph. And my f of x values are going up to 30. Now, my graph here is only going up to 15, so I'm just going to write times 2. And so we're going to kind of rescale our y-axis. So that 15 here at the top is actually my 30, just so I can make a picture. All right, so it says, so we have these values in the table. What is an approximation for this integral using a right Riemann sum? So let's think about that. Now I'm going to make a picture just so we have a visual of what's what. So when x is 2, f of x is 12. So that means we're at this point right here. When x is 5, we're at 28. So 5 is at 28, so way up here. When x is 10, we're at 34, so we're actually off the graph just a bit, right up here. And when x is 14, we are at 30, so we'll be right here. Now here's the thing. We really don't know what happens in between. I mean, what we could do is say, oh, I bet there's a really nice curve that connects these points, and maybe there is. Or maybe we have this going on. We really don't know. All we know is that we have a continuous curve. That's all we can do, but that's it. So we can't make assumptions about what happens in between these 4 points, but we can still make an approximation with rectangles. And it says we're using a right rectangle. So that means in between 2 and 5, for example, my rectangle is going to touch in the upper right corner. So even though we know that at 2, we're down there at 12, we are using the upper right corner to make our rectangle. So between 2 and 5, I'm going to be using 5 as my height. Then we go from 5 to 10. So between these two guys, I'm going to be using 10 as my height. And between 10 and 14, I'm going to use 14 as my height. So what I've basically done is created 3 rectangles where each time the right corner, the ones I'm making red right now, are determining the height of my rectangle. So could you find the areas of these 3 rectangles? And the answer is, of course you could. Let's figure it out. So let's think about this. The x row is going to find my widths, and the f of x row is going to find my lengths. All right, so first rectangle. How wide is it? Well, we're going from 2 to 5, so it has a width of 3. And then remember, 5 decided how tall the rectangle was, so that's going to be 28. First rectangle, 3 units wide, 28 units tall. The next rectangle goes from 5 to 10, so we have a width of 5. And remember, the right side determined the height, so the height is 34. And then for the last rectangle, we're going from 10 to 14. So that is a width of 4. And the right side decided that the height would be 30. So very simple. 3 rectangles. Here we go. So now we just have to do a little number crunching. So 3 times 28 is 84. 5 times 34 is 170. And 4 times 30 is 120. So now we just add these all up for a grand total of 374. And so that is our estimate for this integral, even though we never even had a function. But based on the data we were given, this is our estimate for the area under the curve. Is it a good estimate? Who knows? We really don't know anything more about this function other than it's continuous. So we did what we came to do, but we were actually able to estimate that area. So in this problem, f of x doesn't really have a real life meaning, but let's say that it was a velocity function, right? If f of x were velocity, and let's say that the x-axis is in hours and the y-axis was in miles per hour, you just found out how far you traveled, 374 miles. And that's your estimate. Could be too big, could be too small, but at least we were able to get an estimate. So that's ultimately where we're going with this idea of area. So I've taken us a little bit further than the videos you saw did, but this is the idea of what calculus can do for us. It opens so many doors. So with that, I'd like to close this 4-week experience with you by hopefully giving you a quote that makes you say, yeah, that's exactly what we saw this week or this month. Calculus works by making visible the infinitesimally small. Everything we have learned has been about infinity. Usually it's about making something really, really small so that we have accuracy, whether it's finding how fast something is moving or finding how far something went. That is awesome. So I hope I've given you some things to think about when you get to your actual study of calculus that help you appreciate why this subject is so amazing. And for our final little cartoon little thing here, I want you to take a look at the integral at the bottom of the page, because isn't that what life is all about? Life is our experiences all added up from birth to death. Pretty cool. You guys are all much more calculus smart than you were 4 weeks ago. I will see you on Wednesday. Have a good one.